Can you tell the difference between these two functions? They are different. If you look, well, other than obviously the syntax, did you know? I didn't even know you could do this in Rust. It lets you define functions inside of functions. Yes, this is valid syntax. I was just so surprised to see that you could define a function inside of a function, which you probably could also define another function inside of a function. This is something that I don't recommend you do ever. You never really need to do this, probably. I can't think of many situations where I've written many Rust applications and I've never had to run it. However, common scenarios is where you might want to use something called closures. In Rust with closures, the idea are functions that can be captured in the enclosing environment. Well, that doesn't really help me understand what a closure is. In Rust, the closure is a syntax that lets you define code in the local scope that has access to variables in the exterior scope. So you can say you can access variables that, like the variable x, can be accessed above that scope. And then you can and then you can define it and assign this sort of a lambda. So if you're familiar with lambdas in other languages, you can use this pattern in Rust. And I have wanted to use this in the early days of Rust back many years ago. I tried this pattern. It couldn't get to it the way I wanted, but it does look like they have a really good solidified closure capability these days. Reading this second sentence here really quick. For example, closure that can capture the variable, the x variable. What is that? What does it mean? It caught the x. It basically means through Rust's borrow checker, which is, the compiler, it's going to check to see where the ownership of that variable is. If you've defined x in a higher scope, so you say let x equal to 1, and then you use that variable inside of a closure in this function here, it's going to move the ownership inside that closure, which means you can no longer use that variable anywhere else except for inside that closure. All right, now we're getting crazy with the idea with Rust and closures. We have the ability to create a self-contained function that has access to all the surrounding scope, but it goes a step further and it gives us this kind of a nice, concise syntax that's meant to be used on the fly. So if we're reading our documentation here, the syntax and capabilities of closures makes them very convenient for on-the-fly usage. Calling closure is exactly like calling a function. But there's a difference. The syntax is a little bit different. The input and return types can be inferred, which is great, which means that we don't have to worry about saying what the output's going to be. So let's take a look at what that looks like. So that means here in a regular function, right, in a regular function definition, we always have to define what the output's going to be if there's an output. However, with a closure, you don't have to do that. You can if you want. So for example, if we wanted to sort of mimic exactly what a regular function looks like, the syntaxes are almost identical if we really take a look at between the two. So, right, we've got our function that takes in an I32, right, an integer, and then it returns an integer. And so it's like a simple use case, right? We do need a semicolon here, right, on the second one, because we're defining a variable and that this is required. Instead of using our parentheses, we use our bar symbols, and then our parameters are inside the bars, and then everything else is basically the same after that. Due to the nature of having these closures, these lambdas, we want to have sort of a brevity. So you can exclude a lot of syntax, and so this reduces overall syntax, which is great because this is kind of like on the fly. We have a little bit of logic that we want to execute, usually in an iteration, and sort of like a map if you're iterating over list of items, and then you want to execute a function sort of like in a loop. This is a lot easier because it's more concise. And also, if you didn't know, this syntax is valid. So you can define a function inside of a function and then probably another function inside of that. You don't usually need to do such things because even though you can, you probably don't want to. It makes the code complexity a little bit more, and it's just a little too much. So even though this pattern works, probably best to stay away from it. This pattern is fine because we usually are going to have single line functions. There might be cases where you want a few extra lines, which is kind of okay, but if you're starting to get into too many lines, you might as well just define another function and then call upon it. From a code practice, like best practices, you want your closures just to be one line at best, right? Best case, 2 or 3 lines max. Anything further, define another function and then use that function out. Like for example, we would want to do this, right? Let's create another function altogether here. And then we, have multiple lines. And see, what's great about this is then we can also apply unit tests onto this function right here directly. And then it's more componentized. So, and it's also, less indentation, a little bit easier to read. It can have its own Rust doc. There's just a whole bunch of benefits to using this pattern when you have multiple lines. You might as well do that. When you have, a few lines, 1 or 2, use the closure. Closures will capture your variables. They'll just take them. Within Rust, when you're defining a closure, right, sort of like an inline lambda, you will be risking, of course, any variable that is referenced inside that closure from the scope where you've defined that variable, the function, right, the closure. It's going to capture that, and that happens. It's immutable. They'll do it immutably. So it means read only. But it is very important to notice that if you attempt to read from that variable, but also try to access that variable. Again, before you exit, so there's a problem. You just have to be aware of this because it happens automatically. So if we're taking a look here, just real quick, we'll walk through. So closures are inherently flexible and will do whatever is required that you've asked them, including capturing, which sometimes moves and through borrowing or just like capturing, and the ownership will be owned inside that closure permanently, depending on how you've defined the execution. So it'll start by trying to capture by reference, which is read only. It will, if you need to mutate it, it will try to capture it through mutation, which means read and write, and otherwise it will fully take over ownership if it has to. And the good news is you don't have to annotate any of this. It just happens automatically. So let's take a look here. We've defined a string called color, and it's green. And then we create a closure that will just print the color. So it's just like print the color. And this is a read-only borrow. And then we can keep calling this closure. We can call it print, and calling closure using the borrow. So it's going to call color. It's going to use color borrow. It's going to read from it, and then it's going to print. The good news is we can have another read reference, so you can reborrow color and do something with it as a read only, and that's great. You can read from the same value. Specifically because we also it's immutable, right? So we won't need to write to it. We're only reading from the data. And so this great news is that we can, reuse this in multiple spots, and we can keep printing and reading from it. And if you want to fully capture the variable back, it says that we can do this through a move to move it back into scope after the last use of print, right? So the last time we've used the closure itself, and the compiler knows that we are no longer going to be accessing this variable, so you can always recapture it if needed. Here's where it gets tricky. Say we have our own closure that's going to mutate data within the scope, like an incrementer, right? We want to increment a number based on the number of times we've done something. Now we're going to get into danger zone. This stuff that we have to watch out for, right? So we've got a mutable integer that's going to be able to increment numbers. And we define our function, our closure, that increments the number plus equal 1, right? So increment the count. So this number will continue to increment every time we call this. We'll also print that count. So we're writing to the counter and we're reading from the counter. Now, if we attempt to borrow the count, we can't. It says the closure is still mutably borrowed. It's borrowing count because it is called later. An attempt to reborrow will lead to an error. What does that look like on the compiler? We cannot borrow count as immutable because it's also borrowed as mutable. We can't do it. It says, nope, you're not allowed to do it. There's just no option. You just can't do it. It's just like, nope. You cannot make this possible. If you really wanted to, I'm looking into it. If you really wanted to, you could add a parameter here that will return the data without incrementing it, right? So you can have like a reader or increment, right? So you would have an increment function, and then you'd probably say read bool if read, and you can say return count. You could probably do something like that. So then if you really needed to have read access to the counter, you can have the lambda itself. Let's see if that works. I'm just going to double check that the compiler will let us do that. Let's see. All right, I adjusted the code just ever so slightly. If you did want to access the data from a mutable borrow, you could add a Boolean. I said write. If write, then basically increment the number, right? And then otherwise print. But you could also return the number itself. So that could be a way that you would jump in and be able to read and write to data within the captured variable, right? Our captured count. Even though it's been borrowed immutably, you can still use this approach. And then if you wanted, you could just, say increment, and you don't want to write to it, so you'd say false, and then you'd be able to say let current equal this, something like that. But also, Otherwise, we could do this. I suppose we could, and then this would increment the number once, but then you can read from it, and then you can continue to read from it, but it wouldn't increment. And then it compiles perfectly fine. Love this. Not confusing at all. Like variable shadowing. This is our good old Rust variable shadow. Lets you redefine the same variable name and assign it to different data. Also, they have an example here where you can go ahead and recapture the borrow after your last use of the lambda, or of the closure, right, of the anonymous function here. And you can just do that using this approach, but you can no longer use the closure. This is another option. If you know that that's going to be how you want it to be. No longer using this. Okay, let's recapture the count. We've got two more examples here that Rust by example gives us for capturing variables in your anonymous function, your closure here. They have an example where we allocate data on the heap using box. Then we move the data automatically through consuming it inside of our closure. And then we call memdrop. Essentially is like saying goodbye to the variable, and you can no longer use it permanently forever. It's gone, and you can never use it again. So it's consumed once, and if you try to consume it again, the compiler will give you an error saying, nope. Use of a moved value, consume, which is, the name of our, well, interesting. Consume moved due to this call. I was going to think that it was going to say movable consumed. Why is it saying consume consumed? Wait. Closure cannot be invoked more than once because it moves the variable movable out of its environment. Okay, this is what I was expecting it to see. Since we're executing this twice, it won't let us. We're attempting to execute it twice. Rust is saying, nope, sorry, you've dropped the data and you're accessing it here. It is no longer accessible. I believe if I comment that out, though, it should be fine, right? Yeah, there we go. Okay. All right. Just checking. Just got to double check, right? There's one last keyword trick. You can throw the move keyword in front of your closure to have the closure permanently and forever take ownership of your data. So you've got haystack, which is a vector of 1, 2, and 3, right? 1, 2, 3. So it's a simple little 3. It's like an array. And then we take a growable array, right? Vectors are growable arrays. We take our haystack, and then we check to see if whatever we're searching for, essentially it's the contains function, is inside. But since we use move, this means that haystack permanently is going to be captured inside of your closure. It's now owned by the closure, and there's no recapturing it afterward. And that goes for reading and writing. So we can attempt to read from it outside of the closure, and that will give us an error, right? If we execute that, it's going to give us an error. It's like, nope, sorry, you can't do it. Value moved into closure. The borrow checker. I love that phrase. It doesn't allow reusing variables after it has been moved. So if you don't want full ownership, you can, so it's describing here, remove the move keyword. So that way in the future, again, you could actually, so now if I execute this code, you will be able to print, I think, right? That should work. It should print out. Yep. Okay, here we go. So it's a nice little way if you want your closure to fully capture any of the variables that are inside of the scope to be held here. It's going to keep it there, and you can't recapture it ever again if you have the move keyword. So it's like a nice way to sort of throw like a permanent lock on that, so you don't. That's the way you program it. You intend this variable never to be used outside of your closure. So it's like a little safety mechanism, if that's what you intend. Otherwise, you don't need to use it.